if we look at this picture, we can use something that's called breadth first search algorithm that we have discussed earlier in other lectures. So if we start from Riga, we can first go to all the members or all the children that Riga has, all the linked nodes that Riga has. It's not exactly correct to call them children because it's a graph. We would talk about children if we were talking about the tree, right? So once we have visited all of those nodes, then we can go one depth further. So we can go here to LA. We can try to go here, but we see that DC has been visited already. So we're going to have to check out for visiting. And the same goes for DC. From DC, we can try to go there, but we see that LA has been visited already, and that New York also has been visited. And then finally, we can go to, from LA, we can go to Vancouver, right? And that way we have visited the whole graph. We have visited all the nodes in the graph, right? By walking through the graph. This is called breadth first search. Perhaps a better representation of breadth first search would be if we, let's say, if we had a tree, we can first go to all the children of the root node, and then we go to all the children of these nodes, and then we can go to all the children of these nodes if there are any children, and if there are none, then we don't go there, of course, right? So in breadth first search algorithm, the way we do it, we descend one level first, and then we descend one level more, and then we descend yet another level, and then we may descend another level if we have more stuff to look to search for. One application of breadth first search might be find. So let's find if we have a vertex v in our tree, right? We could use breadth first search until we stumble upon v. So let's say v was here, and then respond to whoever called us that, hey, yes, there is a v, and all is good. If v was not in this graph, then we would walk through the whole graph, we would not be able to find it, and we would respond, hey, we couldn't find anything. Okay, so we could use breadth first search for searching for items, for finding items whether they are part of the graph. Now another note is that you might tell, well, this is a tree, right? It's not a graph really. And there are two things about this to be said. Tree is also a graph, but even though it's a tree, you could imagine that there are more edges in that tree that link those nodes at different levels, perhaps somehow, that we don't need to actually walk because we have visited those vertices already. Okay, we'll see how it works when you actually program breadth first search. Okay, and that is what we are going to do next. We are going to program breadth first search algorithm on that data structure that we have created already. All right, so let's do it. What do we need to add here? So in my code for testing the graph, I may want to call a function BFS find. Okay, BFS find. And I may look for a vertex, some vertex v. All right. Okay. But of course, this vertex has to be a concrete value, so it's not going to be an arbitrary v, but we would be looking, let's say, for LA. I want to see whether LA is in this graph or not, right? But I may also need to specify the vertex that I want to start from. What is the route that we want to start searching from? Okay, so I'm going to say let's start from Riga and let's look for LA. Okay, so that's going to be my my call here. All right. Okay, so apparently we need to define another function in our graph, which is going to be called BFS. BFS find. To be more exact, it's going to be a function, and it's going to have two parameters: start node of the type V, and target of the type also V, right? So what is it going to return? For now, let me just write unit there, but we may think perhaps later on we may want to return the path actually that it takes to get there, right? But for now, let's deal with only the breadth first search. Let's try to walk across the graph and see if we can actually manage that. All right. So let's do it. Sometimes in the literature, you call these things by different names. It could be start or target, or it could be source, SRC, let's say, and destination. Let me call it DST. Okay. So let's stick to that, for example. But we need to talk about the algorithm of breadth first search. So let's create the breadth first search function first. Okay. And I'm going to change that here as well so that we're on the same page. And later we're also going to create another function which is going to be breadth first search find. Okay. All right. So the algorithm, how do we implement breadth first search? And the idea here is we will start with the node R, okay, and we will look for the rest of the nodes. In order to do breadth first search, I'm going to create a data structure that lists all the nodes that we have visited. All right, and we will have another data structure with the nodes that we need to visit. When we start out, when we have our BFS with our start node, which is R, and we will be looking for the node L, for example, LA. All right. First, we enter the node R in the list of visited. And perhaps it's even more makes sense if we switch these guys. Then we try to see from R, where can we get to? Okay, so let me try just a blue color. We start with R in the to visit list. From R, we can get to N. Let's add N to the list of nodes to visit. And then we can also get to the node D. Let's add that one to the list of nodes to visit as well, right? We are done with the R, so we can take it out, right? So in fact, we could take out R whenever we start considering it. So I should have taken out R first, and then we add these guys. Once we take out R, then we enter it to the visited list. The next one to take out is N. So we take N out and we add it here to the visited. And from N, we can get to LA. So we're going to add LA to the nodes that we need to visit. We need to explore them. And we check out, okay, we can get to the node D, but D is already part of the to visits. So it doesn't make sense to add D one more time, right? So we notice that whenever we add the node to this list, we need to check whether that node is in there already. From N, in fact, we also have a path to R, to Riga. But we should check whether we visited Riga already, because we did. Right? So once again, we need to check all the nodes that we are considering to adding to the visit, whether we have seen them already or not. And then if we have not seen them, then we add them to the toVisit list unless they are there already. Okay, so I hope that you are getting the point. So we are done with N. So the next node to add would be D. We move it to visited nodes. From D we can go to Riga, but Riga is in the visited, so forget it. To N, but N is in the visited, so forget it. To L, LA, so it's not in the visited list, but it is in the toVisit list. Okay, so it's already here, so we don't need to add it one more time. Okay, cool. We're done with D. And then finally, we take out L, and we see where can we get from L. We can get to N, but N is here already. So we need to add L, of course, to the visited because we are dealing with it now. We can get to D, but we have seen D already. And we can get to V. So V needs to be added to the toVisit list. Right? And we are done with L. Right? And then finally, we take L. We are done with L. We take V. Okay? So the very last node to take V, we take it out from the toVisit list. And where can we get to? We can get to L, but the L is in the visited list already. Okay? And that's it. We cannot get anywhere else from V. So we're done with V. And then we're trying to get something out from the list toVisited, but toVisit is empty. Okay? And that means we are done with breadth first search. So what this whole story means is it kind of outlines the algorithm how we should create it. What kind of data structure should we use for toVisit and visited list? We could use list, but it might not be the most efficient way to do it. So therefore, I propose that we use for the visited nodes, we're going to use a set. Okay? And for toVisit node, since we are adding to the end and we're taking the next node that has not been processed yet, there's a data structure and it's called a queue. Since we're going to be changing the values for the set, we're going to be adding to the set, and we are going to be adding and removing values from the queue. Both of these data structures have to be mutable. So we should be able to change the values. So that's another aspect, right? So now that we have established that these are the data structures we should be using, let's go ahead and use them. All right? So let's go to the code. We need to add a queue and we need to add a set in our code. Okay, and in our code for the BFS. And so let's say it's going to be a value because we're going to need it only once. So toVisit. That's the first data structure, and it's going to be a queue, as discussed earlier, and a mutable queue. All right, and we should have a type for it because we need to specify what kind of items we're going to enter there. We are going to enter vertices V. Okay, and now that we have that, let's create a new queue for that. Right? Mutable queue. So that we have an empty queue to start with. Okay? And we also need another data structure for visited, which is going to be also mutable. Set of the type V. Why do we use set? Because the order of elements in it is not important, but what's important that there's only one element from each of kind of elements in that set. So that's a nice property that the set provides. Okay, so now that we have these lists, there's empty lists, we can work on writing our algorithm. Okay, so we start out by entering the source node in the toVisit list, right? So how do we do that? We write toVisit dot enqueue, and then the element we add is src, the starting element, right? Okay. Now that we have it, now we can have that loop. Remember in the picture we had this while loop. While toVisit is not empty, let's do our business. Okay, so while you could, by the way, write not toVisit dot empty. Okay, and have a loop. But turns out there's also another function which is called not empty. So what do we do in the list first? If we look at our picture, the first thing we did, we took out the node from the toVisit queue, and then we looked for its neighbors. All right. So let's take out the first node. So let me say v0, it's going to be a value, is equal to toVisit.dq. So we need to walk through all the edges that this node has. So therefore, we're going to look for edges of v0, all the edges that this node has, right? And we're going to need a for loop that actually goes through edges. And I'm going to say that this vertex v gets vertex from the edges, and then we're going to check whether this vertex has been visited yet or not. All right. So if we have seen v, in other words, if visited dot contains, so that's a function for the set to check whether we have that in our set or not, contains v. If it contains, then we don't have to do anything. So if it does not contain, so therefore I'm going to place not in front of it, then we actually need to enqueue it. We need to add it to the toVisit list, or queue rather, right? So toVisit, so that we can visit that node later and see the send further down to its neighbors. toVisit except enqueue the node v, right? And we need to mark that we have visited that node. Okay, and that's actually very elegantly for the set. We can add a new one like so, plus equals v. All right. Okay, so what I have done here, I have programmed depth first search algorithm, or I'm sorry, breadth first search algorithm that walks through all the nodes. All right, and whenever we visit a node, then we may, for example, I'm thinking, how could we track the performance of this algorithm? How can we monitor it or debug it? So we could add some print statements here. So let me do that. So perhaps one thing to print would be as we are dequeuing nodes from toVisit and dealing with them, maybe we can print, and that way we'll print all the nodes going through the graph. Okay, so let me add print. This is just for illustration purposes, right? This is not part of the BFS algorithm. Okay, so let me actually add some spacing around it. And let's say that this is BFS, breadth first search. And let's also print that node. Okay, so let's print v0 to string. All right. So what I did in the test main, I called BFS with a starting node and end node. So let's try to run it. Let's try to compile and run it. So it's compiling and saying, hey, there's a problem. Expected but colon found. Expected semicolon but colon found. And the answer is simple. I did a typo. Instead of colon, I should have typed the assignment statement because I really wanted to create these. So sorry for that bug, but thankfully to the compiler, we caught that one. Okay, so let's try again. Let's compile it and run it. And it did compile, it did run, and after printing done from the print nodes, we try to BFS, and perhaps we can comment out the print so that we can see only the information that we are interested in. That's coming from the BFS. And now we can see that from BFS we get all the nodes visited in the following order: Riga, DC, New York. So let's see, Riga, DC, New York. Then we have the LA. We have LA. And then apparently Riga gets visited one more time. Okay, so note that we have a problem that we have Riga twice here, which should not be the case. So apparently we have forgotten to do something. I think that we have forgot to mark the source node as visited at the very beginning when we enqueued it. Right? So therefore I'm going to also add the source node to the visited list, or visited set rather. Okay, and let's try now if it works. So let me compile it, and now I can see that yes, Riga is only once, every other city is only once, and we have walked through the whole graph from Riga, DC, New York, then LA, and then the furthest one is the VC. Okay, so apparently the breadth first search works now, and this is how it works. I'm going to comment this guy out. The next question might be, how do we find something? How do we find that destination node that we actually never used yet? Okay, so for that purpose, I'm gonna rename it back to find, as I intended initially, find. And let's go and search for that node to see whether that node exists or not. Okay, and we could, let's say, if it finds the node, we could either return true or false if it found or not. Okay, so but even more interesting would be if it would return that particular vertex that it found. Okay, so let me just let's keep it Boolean for now. Okay, and then we can upgrade this solution to the one that actually prints something. The question is, where should we check whether the node that we are looking for is found or not? And I think the right answer is oh, there's something red showing, so we'll see. The right answer is that we should really check for that whenever we dequeue a node. Okay, so I could add if the dequeued node v0 is equal to the one that we are looking for, to the destination node, dst. Well, if it is, then we can found it. Then we could, let's say, print line, let's say, found it. Okay, and we return true, because there's no point searching for more if we have found what we were looking for, right? However, if we went through the whole graph, then we need to return. So this is the while loop, I guess, right? Right. So if we went through the whole graph and if we didn't find that node, then we would have to return false. Okay, except with all lowercase for Scala. Okay, Okay, so let's let's try it. All right. So now that it returns something, we could actually print that thing, whatever it returns. So we could do print line, and let's say the same graph, like so. Okay. And let's try to run it now. Let's see if it works. Let's see if we can find LA. And it says, yeah, found it, true. Okay. Let's try to look for something that we cannot find. Let's try to look for some node XX. But for XX to be a valid node, we should actually create that node. We should create that vertex, add vertex. So let's say there's this XX vertex, unknown vertex, that is not linked to anything else, and let's try to find it. Okay, let's try to find it starting from Riga. Okay, let's see. So we see true and false. So true was for this test. Let me comment that and run again, just to have a clean experiment. And down false, yes, XX we cannot find. What if we start from XX? Could we find XX? Let's run it now. Yes, true, we can find XX. What if we start from XX and we look for Riga? False, we cannot find Riga. Because if we look at our map, the XX is living somewhere outside, somewhere completely not connected, I don't know, in Greenland somewhere, or wherever it is on the map. And there are no flights to that place, unfortunately. All right. So to recap, we have created a breadth first search algorithm that walks through the whole graph and looks for certain node. So that's what our breadth first search find function does. And it returns whether it has found that node or not. One last thing in this story would be to actually change that algorithm in the way that I'm going to get rid of the print statements. That rather than printing that it found it or returning true or false, if it finds it, it will return that node, v0, for example, right? If it does not find anything, it will return null. So that's one practice how you could do things. You try to find things. If you don't find anything, you need a special way to tell the caller that nothing was found, and often people just return null. It's not a very good practice, and I'm going to comment on that in a moment. So let's try to actually run it. So if we try to run it, it says that null does not match the type V, type mismatch. In fact, no, it complains about V0, that V0 does not match V. Aha! And the reason is because I have not specified that the return type is V. Okay, so now the return type is V. Now let's try to run it. And now it is complaining about null, that null cannot be of the type V. Null is of the type null, right? And Scala is very particular about it because it's trying to enforce the correct way of programming, okay? And therefore, if you really want to return null, if you really want to do that kind of protocol when you return some type, some object when you found it, and you return null or some sort of sign then that you did not find it, then you could actually return a different type. Let's talk about option. So option is going to be a type with a subtype of V. And the thing with the option is that if we don't find anything, then we can just return none, which is part of the option. if we found something, then we would have to return sum of that particular element. All right. So let's try to run the code now. Let's remind us what the code is about. We have the BFS find. We are looking from Riga to LA. And let's see what it's going to print if we're looking from Riga to LA. It returns some LA. So apparently it found LA. Now let me try to look for something that does not exist, for example XX, and let me run it again. Then it returns none. Okay, so I think this is a good point to make a break and to say that we have created a class for graphs that adds vertices, that adds edges. And we have created a breadth first search walk through the graph that looks for a certain destination node and returns that node if it finds it, or returns none if it does not. All right. So there are still more questions, I presume. What if we want to actually add weights to those edges? How many hours does it take to fly from Riga to LA, for example, and so on? For that, we're going to need a slightly different graph, which is called a weighted graph. And we can discuss it the next time.